So what we're going to calculate now is a reactive circuit. So we're going to look at reactive capacitance, and that's represented by the letters X, big X, small c. And XC is equal to 1 over 2 pi FC. Now the reason we call this reactive is because, unlike before where it was just DC, with these, the frequency, we're using AC waveforms. So imagine we have a circuit with an AC waveform and a resistor, maybe 100 ohms, and a capacitor. And this is going to be 47 microfarads. Big F because it's the name of a person. Now we're going to be putting a fairly low frequency through here. So this is going to be sort of typical mains voltage, 240 volts and 50 hertz. So 50 cycles a second if we had a sine wave here. Well, our Ohm's law doesn't apply here because this is a reactive circuit, it's got reactive components in. So we need to calculate what XC is. And XC is like the equivalence of a resistance at that frequency for that capacitor. So in this case, XC will be equal to 1 over 2 pi times 50, the frequency, times 47 times 10 to the minus 6. That gives us 67.72, and the unit for this is ohms, just like resistance, but it isn't quite like resistance. We measure it in ohms, but it's not quite like resistance. Now normally, if we knew that this was the resistance of this capacitor and this was the resistance of this resistor, we just add them together and we'll be on our way. But we can't do that with reactive circuits. It's not quite that simple. In fact, if we wanted to work out I, the current in this circuit, I is equal to V. Instead of being over R, it's equal to V over Z, where Z is equal to the square root of R squared plus XC squared. You may notice this from Pythagoras. It looks the same, doesn't it? Because it is, and we'll see why in a bit. So we've got here 100 squared plus 67.72 squared. And that equals 120. And again, 120.77 ohms. So now we can use this for this calculator. I'll just draw a line so we keep that separate. So we've got our voltage here, 240, divided by 120.77 gives us 1.98. Actually 1.99 if we round properly. Amps. So that's the total current in this circuit, is 1.99 amps, 1.98, 1.99. Then from there we can calculate the voltages across both of them. So we know the current, we can calculate the voltage across them. So we'll call it VR, the voltage across the resistor, has got to be equal to I times R, which is equal to 1.99 times 100, which equals 199. And then VXC is going to be equal to I times XC, which equals 1.99 times 67.72, which equals 134.57. In both cases, volts. Now we can see here that the voltage, the sum of the two voltages, doesn't add up to 240, and this is pretty typical of these reactive circuits. This is why we use them for things like creating sparks in spark ignition engines like petrol engines. Let's have a look at the simulation. So an AC voltage, always need a ground. So I think we said that this was 240 and frequency was 50 Hertz. And then we had a resistor of 100 ohms. And then we had a capacitor that's under the same compartment in there. Put the capacitor in, and I think we said this was 47 micro. I'm going to leave the micro symbol there. So that's at 47. If we use the down key, it'll keep moving us down to milli. 470, 47 micro, use the down key, that's it. And then wire them together. Obviously, as soon as we put the ground in, this bottom node will jump to 0. So, we need to put some meters in. Let's put a current meter in. Pull this back to give us some space, because we're going to need to measure voltages in a minute. Move them as well. So now when we run it, we can see that it's going all over the place, and that's because the voltage and the current are constantly on this sine wave 50 times a second. We can't see that. So what we need to do is, when we're looking at this, is change it to periodic. So then it'll measure the features of the period of the sine wave rather than continually. It'll still do some continually. So peak to peak current is 3.97. Now if we think 3.97 is practically 4 amps peak to peak, and we worked out before, we just worked out just the peak value, which was from 0 up to the peak of the sine wave. You can see that better actually with the graph. Let me just auto that. So this is the graph of our current. We're seeing the whole thing, but when we did our calculation, we were only calculating from 0 here up to the peak, which is 1.99 practically. But here we've got the full waveform, and our meter here showed the full one. Okay, so let's have a look at a voltage across the resistor. So put our voltmeter in. Now remember, this is going to measure the voltage across the whole thing. So we're going to need to put a reference in, and we need to make sure that PR2, the voltage meter, has a reference of Ref1. So it's measuring from there to there, not from there to ground, which is what it would do otherwise. And also set that as periodic as well. So we see here that the peak to peak voltage, in fact we can look at it on the graph. You can see here peak to peak voltage from here is just shy of 200 from 0 to peak, and if we look back at our calculation, we got a voltage of 199, just shy of 200. So we're good on that one. Let's put some more voltage meters in as well. Let's go back to our schematic. In fact, we could just use these ones if we wanted to, drag them off, put them to the other side. So all we need to do now is just make sure that this is set to ref 1. It is still. So now we can take a reading. And now if we look, we've got peak to peak of 268. We go and have a look at the graph. That's the current. We can turn the current one off. So if we look at this, the peak here comes up to about 134, which is half of 268. And if we go to our calcs, 134. So this has perfectly represented our calculations. What we may also be interested at this point, we said earlier that this here looks a little bit like Pythagoras. Well, it is. And what's happened here is we've got, if we were to draw XC on a graph versus R, it should be straight. Let me do a better job of that. So if we to draw it here, where we've got XC up this graph, this axis, and R here, well, our value of R was like 100, wasn't it? It was 100 ohms. And our value of XC was 67.72. Now if we were to draw a line between these, draw a line up to there, then the length of this line would be Z. And obviously this is where we got Pythagoras from here. And this is how we calculate it. We've got our real part here, our resistance, and our reactive part here at the side. And then we've got this angle, which we call a phase angle here. And we could work that out just from our Pythagoras, the phase angle. This angle is equal to the inverse tangent of the opposite, which in this case is XC, over R, our adjacent. So we can calculate this while we're here, and that comes to an angle of 34.10 degrees. We've got our voltage like a sine wave, and we've got a current that's occurring out of phase with it. The current's coming before. Now we know that power is equal to V times I. Well, this works really well when current and voltage are in phase with each other, because when they're in phase with each other we get a voltage like this, and we get current happening directly on top of it. So we just multiply the peak of the voltage by the peak of the current and we get the power. But here, we can see here the currents are very low when the voltage is high. So when we multiply them together, we don't get an amazing amount of power because the current and voltage are out of phase with each other. We have problems, and we can see this when we go back to our, if we were to put both on together, and I put the current back, they're on different scales, so the current scale is over here and the voltage scale is over here. But we can see that the current is leading the voltage. So the current peak is happening here and the voltage peak isn't happening until here. And if we were to measure this, it would be 34, what we just did the calculation for there, 34 degrees out of phase.